All right, folks, welcome to our official lesson today. Like I talked about earlier in class when we met for the first 5, really the goal for today is just to let you work at your own pace, do a little bit something different for math class, so we're not doing the same lesson over and over and over again. I'm just going to remind you, you really have 2 things to turn into me before the end of the hour. First is this basic 20, that Schoology quiz where you just plug in your answers, and that is due by the end of the hour. You get unlimited attempts on it, and the questions are pretty short. So I would imagine it would take you maybe 20 minutes total, maybe a little bit less if you're really cruising through it. After that, watch this video. And then the third thing, this is your homework for next time, is a geometric probability worksheet. I do think you could get all 3 done in 90 minutes. It just kind of depends on the pace that you work. Just make sure you're turning in this guy and you submit this Schoology quiz due by the end of the hour. Last thing that I'm going to say, just check in at your own pace before the end of the hour. So before you wrap up math today, come say hi to me again in the Google Meet. At the very least, you could tell me what you're doing for the weekend. Otherwise, I will gladly answer questions and just kind of see how this whole thing went. I'd love your feedback. So basic 20, get that done first. Watch this video, and then you have a geometric probability worksheet that will be due next class. Just make sure you check in for that last 5 before you leave. Goals today, being able to solve probability problems. We're going to talk a little bit about what we did last time, and then determining the area of various shapes and kind of combining these two and see what happens when we have probability problems that involve areas. So let's get started right away with those areas. These will be the 3 main shapes we are going to talk about today. Hopefully you remember some of these, or at least they're familiar from geometry. We have circle, which is the area of a circle is pi r squared. We have the area of a rectangle, which is length times width. And then we have the area of a triangle, which is 1/2 base times height, or 1/2 length times width. Oh, I forgot to say, you guys, this video is brought to you by Flamin' Hot Cheetos. No, they don't actually sponsor me, but maybe one day they'll see this and they'll start sponsoring me. I don't know, it's worth a shot. Or maybe I'll get some free Cheetos out of the deal. Who knows? If you know a guy at Cheetos, send them my way. Real quick, just to give you some examples, I'm going to save the circle for last here. Just to kind of get you back familiar with using these formulas. The area of this triangle, would be 1/2 base times height. So my area would be, evaluating this first, would be 3 times 3 would be 9 units squared. The area of this rectangle would be length times width. 3 times 5 would be 15 units squared. And then the thing about this is you would get a decimal answer if you do the area of this circle, right? Because we'd have pi times radius squared, which would be pi times 3 squared. You may have had teachers in the past that ask you to type in 9 pi to your calculator. Leave it as 9 pi today. Leave it as 9 pi for me when you have me as a teacher. This is called exact form. And it's such a cleaner way to write numbers as 9 pi. 9 pi is fine. There's nothing wrong with that as an answer. In fact, mathematicians consider that very exact because you don't have to worry about rounding or anything like that. So I would write this area as 9 pi units squared. Today, if you have a fraction with pi in it, if you have an answer with pi in it, that is just fine. So let's start to apply this to probability. Last time we talked about probability being the number of ways something can happen divided by the total number of outcomes. So if you think about, like, I want to roll a die, and in order for me to win, a 6-sided die, in order for me to win, I need either a 4 or a 5 to pop up. So the total number of ways that I can win what I want to happen is 2. And the possible outcomes, all of the possible outcomes of this roll would be 6. It can be 1, 2, 3, 4, 5, or 6. So what I want, the outcomes that I want to happen, divided by the total number of possible outcomes. If I apply this to geometric probability here, you can kind of see my leftovers from the first time I attempted to record this video, is I have the area of a desired region divided by a total possible dartboard. So that's kind of like the classic example with this is, imagine I have a rectangular dartboard here, like at a carnival or something, and I win by throwing my dart in this shaded region. So the probability of you doing that, assuming your dart lands randomly, would be the area that you want, aka the shaded area, over the total area of that dartboard. Another like example I could think of, if you've ever seen the show or the movie Hidden Figures, which is about 3 women like breaking color barriers, doing awesome things as engineers. It's a really good show. You should watch it. It's on Disney Plus. Is one, like the main character, they're sending a rocket into orbit. So here's my rocket. Look at that. Wow. I should be an art teacher instead. They're sending a rocket into orbit, and then it circles the Earth, and then it comes crashing down, and the Navy needs to go pick it up, right? The little capsule where the astronaut is in. And so she has to come up with a probable landing area, right? If the rocket goes up, it hits orbit, and then it comes back down. She has to find out where in the ocean is that going to hit so the Navy can go rescue the guy. And so she does all these calculations. She figures out where's the release point on Earth's orbit so the guy can say, okay, I'm going back down to Earth, and then he lands in her geometric area. So that was another example that I could think of right off the top of my head. So if we go back to this, go back to our first problem. The area that we want here is the area of this blue triangle. And that area would be 1/2 the base of 5, this guy is 5 down here, times the height of 7, which would be 2.5 times 7. Times 7, which would be 2.5 times 7. I would pull out a calculator here, which I'm doing on my phone, and I would get the area that I want it to hit would be 17.5. The total possible area that if I throw this dart at random would be this green rectangle, and that would be an area of a rectangle is length times width. My length here would be 5 again, and then my width, my total width would be 11. So the total possible outcomes would be 55. And so you would say the probability of me throwing a dart would be 17.5, the area that I want to hit, over 55 units squared. You could turn that into a decimal. That would be fine. You could turn that into a percentage, but you can also just leave it as a ratio, leave it as a fraction. Okay, let's keep cooking here. The area that I want over the total possible area here. Yeah, these get a little bit more interesting. They get a little bit more involved as we start to think about kind of cutting shapes out. And we'll talk about that here in a second. But this one, it follows the same thing. The area that I want is that little square, which would be 3 times 3, which gives me 9. And then here is where you can leave this as a pi, as an exact form. So you'd have pi times r squared. So this would be 100 pi. So you can write your answer to this guy as 9, the area that I want, divided by 100 pi. And that would be a perfectly fine answer, right? We have the area of the square divided by the area of the circle, and we are good to go because the circle is my total shape. Okay, got a couple more examples here for you. Now let's think about this problem. So I got a little bit ahead of myself in the last one. This is the one where you have to start cutting some stuff out. So if you think about it, this is a pretty good carnival game to play because you're probably going to win, right? There's just a little bit of a space that is going to keep you from winning. And that is that circle on the inside. So the area that I want would be that area of the entire rectangle here, except for the area of the circle. So the shaded region can be represented by the total rectangle minus the circle. And then my whole dartboard that I'm playing with would just be that area of the rectangle. So the whole dartboard that I'm considering is this rectangle. Let's do that first. The area of the rectangle would be 15 times 6, which gives me 80. And then the other area that I need to figure out in this problem is the area of the circle, and that's pi r squared. The area of the circle is pi times 1 squared, which would just be 1 times pi, or pi. So now if I plug everything into this probability formula, I would have 80 minus pi, right? That would be this green area that I want to hit, right, outside the circle. And then my total area is 80 units, right? This pink area would be everything including the circle, which would be 80 units. And like I said, this is just fine as an answer. You can leave it in exact form. 80 minus pi over 80. Okay, so similar thing here. It's kind of reverse, where you're really cutting out some areas that you don't want. Our probability is going to be the area of the whole triangle, right? That's what I want to hit, minus 2 areas of squares, because we can see that they're the same square. So I'm going to consider this entire triangle as a win, except for if I hit one of these 2 squares. The whole dartboard that I'm considering the total outcome would be the area of the entire triangle. So let's find our areas. The area of the triangle would be 1/2 that base of 14 down here times the height of 12. This comes out to 84 when you multiply it out. 7 times 12 would be 84. And then the area of one of those squares would be length times width, or 4 times 4. So 16. So now if I start to plug in stuff that I know, the area of the triangle here is we found to be 84 minus 2 times 16, because I have 2 squares there, all divided by 84. It would be a good idea to simplify this guy. I'm going to move him up a little bit. So we'd have 84 minus 32 over 84. So that would give us 52 over 84. So the probability that we hit the inside of that square would be 52 over 84. If you can simplify, please do. Right, this would be 26 over 42, or 13 over, gotta do quick mental math, 21. But technically all of these will give you the same decimal, the same percent. So we set up the area that we want, the shaded minus the squares, divided by the entire dartboard, plugged in what we knew, and then we simplified. Okay, last is some word problems that you might see here. Got 2 more problems to go through. And this, I would say, if you don't have a picture, please draw one. It's going to be super, super helpful to draw a picture here. So we have a roof that is 25 by 30 feet. And so we can answer this first question, what's the area of the roof, right away, right? The area of that rectangle would be 25 times 30. And this comes out to be 750. Inside that roof, we have a pool, and the pool has a diameter, so the whole thing across is 12, meaning the radius would be 6. So the area of this pool would be pi times radius squared which is pi times 6 squared. So that guy is going to be 36 pi. And again, you can leave it like that, and that is just fine. What is the probability that this guy lands inside the pool? Well, we just found this area to be 36 pi. So want divided by total, and this would be the probability that he lands inside the pool. The probability that he lands outside the pool, we kind of have to flip this on its head. Well, outside the pool would be this entire rectangle minus the pool itself, right? So 750 minus 36 pi would be the area that I want. And then the entire area is 750. Okay, last one here. You were playing darts with a friend. You have this dartboard here on the right. It's so funny to me that all of these are assuming that a dart is thrown at random, because that feels like when I play darts, just really going to a random spot. And we just kind of have to break this down. We have lots of information here up in the right, and we just kind of got to think this through. So the first question says that a dart lands in any one of the circles. So assume that this dart hits a circle sitting inside this rectangular dartboard. So the dartboard that we can see from this word problem is 24 inches tall and 30 inches wide. So the total possible area that I could hit, the area of the rectangle, would be 24 times 30. The probability that it hits that dartboard would be any circle. So really we're going to consider if it hits circle D. We know that circle D has a radius of 10 inches squared. So the area of the entire dartboard would be pi times 10 squared. This guy is 100 pi. And I'm now realizing I never multiplied 24 by 30 for you. That guy is 720. So the probability that this guy lands somewhere on the dartboard would be the area that I want, 100 pi, divided by the total possible area on that dartboard. So 100 pi divided by 720. The probability that a dart makes a bullseye, well, the entire board is still going to be the area that we could hit, right? So this area of that entire rectangle is going to stay. The only thing that changes now is I want to only consider a bullseye. So this little purple square. In circle A, so the area of the baby circle, has a radius of 2 inches. So this would be pi times 2 squared. So we'd have 4 pi. So this guy, the area that I want, 4 pi divided by the total area of 720. Okay, last one. What is the probability that it is specifically in section D? We would have to find what is the probability that it hits that dark shaded region on the outside. So only section D would be right here. Now this one's a little bit tricky. It kind of involves two parts. The nice thing is our total probable area is going to stay the same as 720. Right, so the area of the entire dartboard is 720 inches squared. The probability that it hits section D, though, if we just really zoom in and we focus on the dartboard itself, would be, oops, I gotta go back to my pen, would be this circle here minus everything inside. So the section we want is specifically that green shaded section is going to be the entire circle subtracted by that pink circle, because we don't want it to go inside the pink circle. We only want it to hit section D. So the area of section D we found above in blue here, and we know the area of section D, the entire thing, would be 100 pi, right? If it hits somewhere on this dartboard, it'd be 100 pi. But we want to take out that area of everything else. So you can see circle C, everything inside circle C would be 6 squared times pi. This pink area is 6 squared pi. So we can get our want area by taking 100 pi minus 6 squared pi. So we would have 100 pi's minus 36 pi. That, since they are similar terms, right, they both involve pi, would give us a total of 64 pi in this green shaded area out here. So we have 64 pi divided by my total area of 720 square inches. So this one would be 64 pi over 720. So those are all the examples I got. I tried to go through them a little bit slowly so you could write down some notes. Again, feel free to fast forward, go back, do what you need to do at this point. I will still be in the Google Meets answering questions. Make sure you get this basic 20 turned in. Make sure you get the geometric probability worksheet started as well. I will see you back in the Google Meet soon. Come ask me questions. Come tell me what you're doing this weekend. Make sure to check in one more time.